Hello, welcome to my channel. In this video, I'm going to talk about an antenna operating in the presence of a reflecting pan. So what is the reflecting pan? Reflecting pans in the field of antenna. Reflecting pan is usually a perfectly conducting pan. So we need to ask ourselves what happens if a electromagnetic wave hit the perfectly conducting pan. So this is the question. So what happens if an EM wave actually singular, hit a conducting pan, perfectly conducting. So you need to ask ourselves first, there will not be any electric field inside the conductor. So no wave penetration in the conducting pan. Another thing is if there is no wave penetrating into the conducting pan, what happens? There will be refraction. And this is all well known. Anyone who have done high school physics will know it. And what we don't normally know is the phase at the interface must be equal for the incident waves, the reflected waves, and also the transmitted wave. So phase at the interface, the phases at the interface must be equal for the incident wave, the reflected wave, because there is no wave penetration, so we have shown the transmitted wave does not exist. So the incident wave and the reflected wave will be perfectly equal in terms of the phase. What happened? So this is one of the important points. Another more important point is tangential electric field will be zero. Will be zero in the interface. So for example, if you have a conducting pan here, if you have a wave source here, then the wave will generate an incident wave. This incident wave will be reflected totally. There will be low wave penetration. So in this case, E I and E R, and then the angle of incidence will be exactly equal to the angle of refraction. Then that's why phase at the interface must be equal for the incident wave and refracted wave. And because of this, we have the angle of incidence being equal to the angle of refraction. So this is it's all very well known. If you have done high school physics, then you will know it. But what is subtle is this point. Tangential electric field will be always zero. So let me explain to you what happened. What is the implication of this point? So suppose you have a source of radiation. So the radiation is the dipole. And the dipole has positive end and negative end. And if you have a refracting plane, perfectly conducting ground plane, so I make sure it is ground, right? Because if it has voltage, right, then the situation could be different. First, the dipole itself will radiate an incident wave, and it will produce a refracted wave, and the angle of incidence will be equal to the angle of refraction. That's all well known. But what is little known is right at the interface, the tangential electric field will be zero. So what does it mean? Suppose you have a dipole here. The dipole has the polarity like this. The positive end is at the top, and the negative end is at the bottom. So accordingly, the electric field will radiate out from the positive end and end at the negative end, just like the battery. So the electric field will point this way and point this way. So if we enlarge this circle, it will be like this. So the electric field, according to here, will continue at the interface until you reach the end. But we previously have already emphasized one point. Tangential electric field is always zero. So what could that be? There must be an image. The image will be formed here. So this is the image dipole. The dipole will also create a current in such a way that it will counterbalance the current about the interface. So the current about the interface is pointing this way. The dipole, the image dipole, will produce another electric field. And this field will counterbalance this one in a way that the total tangential electric field will be exactly zero. In order to do that, the current that is created in the image dipole will have the same magnitude. So if I is the current here, then the current in the image antenna will be also I in terms of magnitude, but the polarity has to be careful. So what happened? You have to produce an electric field in a manner that counterbalance, that cancel off the electric field radiated from the original antenna. So this imaginary antenna will create a field like this. In order to create a field like this, the polarity of the image antenna has to be the same. So if the positive end is on the top and the negative end is on the bottom of the dipole, the physical dipole antenna, in the image dipole antenna, we will end up with the same. The positive end will be nearest to the interface. The negative end will be further away from the interface. So I hope this is clear. This is about vertical dipole antenna. Vertical dipole antenna. And if this dipole is physically small, then we expect the current will behave like this. So E theta will be equals to E theta will be equals to J N K I naught L and then 4 pi R and then sine theta. So the image antenna will behave similarly. The only exception that the distance, if the distance of the original antenna from the ground is d, then we expect the distance between the image antenna and the ground interface is also d. Okay, so this is the case. And if the dipole is small enough, then we expect the electric field will be given by this formula. The magnetic field will be equal to the electric field divided by the intrinsic impedance. Okay, so this is the situation in vertical dipole. But what happens if the dipole is horizontal? That is tricky, but it's not that tricky. We have to remember the last point in our previous discussion. The tangential electric field is always zero. Okay, so now I'm going to draw your attention to another arrangement, horizontal dipole. So now let's take a look. Your antenna is supposed to be like this. The positive end is on the right, the negative end is on the left. So if the ground plane is down here, then we all know that the antenna itself will look like the battery, will operate like the battery. The electric field will originate from the positive end and end in the negative end. So right at the interface, there is supposed to be an electric field pointing to the left direction. But remember from our previous discussion, tangential electric field is always zero. So there must be an image antenna beneath the ground interface. So what happened? So there must be a antenna, image antenna. So the upper one is the original antenna. original dipole. The lower one is the image dipole. In this case, the electric field from the image dipole should be created in such a way that it cancels off the electric field from the original dipole, and this is the only way that makes tangential electric field zero. So in this case, the dipole must pointing in this way. So for the dipole to produce a electric field in a clockwise direction in this case, then the dipole should have a positive end here and negative end here. So in this case, we can conclude that the dipole is pointing to the opposite direction, I mean to the left, while the original dipole is pointing to the right direction. So this is the horizontal electric dipole. Okay? And remember, the current is the same, right? The current will be equals to, the electric field as produced by the Hertzian dipole antenna will be equals to something like this, but the angle is not going to be theta. The angle might be some other value, right? This one, right, maybe a C, right, for example, right? Then you will expect the electric field to be Ki naught L, and then 4 pi R, and then there is another electric field here. First this, and then sine C. Yeah. So this is the electric field. Remember, if the antenna is away from the ground at height of d, then we expected the image antenna to have the same height underneath the ground. Okay. Now we have talked about electric dipole, but what about magnetic dipole? Magnetic dipole. So first of all, I need to talk about what is magnetic current first. Magnetic current. We are going to talk about magnetic dipole. So what is magnetic dipole? Magnetic dipole is the dipole of magnetic pole. So one of the examples is the magnet with N and south. So this is one of the examples of magnetic dipole. Another example of magnetic dipole is when you have a current loop. So like in this case, you have a current here, so you produce a magnetic field, the B field down here. So you will have a B field, and this is the north pole and south pole. So this is the so-called dipole. And another thing I want to talk about is magnetic current. The scientists of the past has tried to correlate the magnetic dipole with electric dipole. What they did was they create another current, so-called magnetic current. The magnetic current is a column of moving monopoles. Moving magnetic monopoles. So suppose you have an AC current in this current loop, then you would expect the B field to be pointing downward and then upward and then downward and then upward continuously forever. And in this case, we expect we call this current as magnetic current. This is an imaginary current. It doesn't exist physically, but we use the concept of duality, the principle of duality, to correlate the magnetic dipole with electric dipole. In a electric dipole, we have electric current. Electric dipole is based on electric current. Magnetic dipole, on the other hand, is based on magnetic current. Magnetic dipole is based on magnetic current. So this is how the previous scientists used this way to correlate electric dipole and magnetic dipole. There is no physical current. There is no such a thing called magnetic charge. But on the other hand, the scientists use magnetic current to supplement this argument. And magnetic dipole is by definition a column of moving monopoles, magnetic monopoles. So from here, the theory of the principle of duality will apply. Okay, now I'm going to talk about image first. This is the core topic of this discussion. The magnetic dipole, similar to electric dipole, magnetic dipole can be vertical or horizontal. So let's say, right, we have a vertical dipole first. Vertical magnetic dipole. So let's say we have this so-called vertical magnetic dipole. Yeah, sorry, right? This is not important. So the dipole itself is the dipole contains the moving magnetic current, a current of magnetic monopoles. So you might have a certain time instant, you have a magnetic pole like this. In order to produce such a magnetic pole, you have to have a loop current, a loop of current. So in this case, the current will be like this. Yeah, by the right hand screw rule. Yeah, then you have a so if the current is an AC current, in the positive half cycle is anti-clockwise. In the negative half cycle, it might be in a clockwise direction, and that's how we produce the so-called magnetic dipole. So what happens if the magnetic dipole is placed just above the ground plane? The reflective ground plane. The ground plane itself will reflect all the electric field. The electric field will not be able to penetrate into the refractive ground plane. So if you have a electric field that has been leaked here, then we expect the electric field will be totally reflected off, with the angle of incidence the same as angle of reflection. Now, in order to have this effect, you have to make sure we know this effect, but another point is right at the interface, the tangential electric field is zero. There is no tangential electric field. And let's take a look here. You have the electric current loop here. Say at certain time instant is pointing this way. So obviously the electric field will be like this, horizontal, I'm not trying to use the isometric view to illustrate the issue. So it will be circular on the ground plane, parallel to the ground plane, So in order to produce an opposite effect, in order to produce a completely tangential electric field being zero, so what we need is to have another counterbalance current. So what we can do is, we have shown another dipole, so-called image magnetic dipole, and it will produce a electric field, but the electric field will be circulating in the opposite direction. So this means the current will be in the opposite direction. So if this is the case, then you will produce a electric field totally opposite. And this electric field will be completely counterbalanced by the electric field radiated by the original physical antenna. So the tangential electric field right on the ground interface will remain zero. So this is the only option. So that's why the vertical magnetic dipole will produce a vertical the current loop will produce a vertical magnetic dipole. In the image, we expect the current loop to be to have current flowing in the opposite direction in a way that it counterbalance the cancel off the tangential electric field. And in this case, the B field is pointing downwards. So we have examined the case of vertical magnetic dipole. What we have not mentioned is the horizontal magnetic dipole. Horizontal magnetic dipole So if you have the north and south pole, if you have a magnetic dipole horizontal, and your ground interface is also horizontal. So obviously, in order to produce this magnetic dipole with the magnetic field pointing to the right, you need to have a current loop. And this current loop has to have a current flowing like this to produce a electric dipole. When you have a current flowing like this, then you will produce a electric field moving this way. the electric field will be a larger loop. In order to make sure you have zero tangential electric field, you need to have an image such that the image produces another current that is producing a magnetic field, a electric field that cancel off the tangential electric field from the original dipole. So in this case, it will be like this. So in terms of the image antenna, it will be like this. So the magnetic current will be flowing into the same direction. The current loop that produces the magnetic dipole will have the same arrangement for both physical antenna and image antenna. So if you have any question regarding this concept, feel free to leave your question to the comment section of this video. Thank you very much.